selective coordination in emergency systems, as required by the National Electrical Code Section 700.27, mandates that overcurrent protective devices be coordinated such that a fault is cleared by the device closest to the fault, minimizing disruption to the rest of the system. The scenario presented involves a 400 amp panel feeding a 225 amp MLO panel, which in turn supplies a 20 amp branch circuit for emergency lights. The challenge lies in achieving selective coordination between the 20 amp branch circuit breaker and the upstream 225 amp feeder breaker, particularly in the instantaneous region where high fault currents can occur. The proposed solution of installing an inline fuse downstream of the 20 amp breaker raises several concerns. Firstly, whether this approach meets the intent of Section 700.27, and secondly, the acceptability of using such a fuse connection method inside a panel. Regarding the first question, whether the proposed solution meets the requirements of Section 700.27, it's crucial to understand the principle of selective coordination. Selective coordination dictates that under fault conditions, the downstream device should clear the fault before the upstream device operates. This minimizes the extent of the outage, ensuring that only the affected circuit is de-energized. The concern with the proposed solution is that the 20 amp breaker may not coordinate with the 225 amp breaker, especially in the instantaneous region. If a high fault current occurs, the 225 amp breaker might trip before the 20 amp breaker, defeating the purpose of selective coordination. Replacing the 20 amp breaker with a fuse does offer the potential for better coordination due to the fuse's faster response to high fault currents. However, simply adding a fuse downstream of the breaker and declaring the fuse as the overcurrent device might not fully satisfy the intent of the code. The entire system, including the breaker and fuse combination, must be evaluated to ensure selective coordination. The code requires all overcurrent devices to be selectively coordinated with all supply-side overcurrent devices. If the 225 amp breaker trips before the fuse clears a fault, selective coordination is not achieved. Therefore, a thorough analysis, including time current curves for all devices, is essential. This analysis must demonstrate that the fuse will always clear a fault before the upstream breaker operates under all fault current conditions. Addressing the second question, the acceptability of using inline fuses inside a panel is a matter of safety and code compliance. While the NEC doesn't explicitly prohibit inline fuses, it does emphasize safety and proper installation methods. Fuses are generally intended to be mounted in fuse holders or blocks, which provide a secure and protected environment. Inline fuses, on the other hand, are typically connected using wire nuts or similar connectors. This type of connection can be more vulnerable to accidental contact damage or loosening, which could create electrical hazards. Firstly, the risk of electrical shock is a significant concern. If an inline fuse is accidentally touched while the circuit is energized, it could result in a severe shock. Fuse holders and blocks provide a degree of insulation and protection against such accidental contact. Secondly, the potential for fire hazards exists. If the connection at the inline fuse becomes loose or corroded, it can create resistance, leading to overheating and potentially a fire. Fuse holders and blocks provide a more secure and reliable connection, reducing the risk of overheating. Thirdly, the lack of physical protection for inline fuses can make them susceptible to damage. If the panel is subjected to vibration or physical stress, the inline fuse could be damaged, leading to a circuit failure or even a fire. Furthermore, the NEC requires that all electrical equipment be installed in a neat and workmanlike manner. The use of inline fuses inside a panel can be perceived as a less professional and less organized installation compared to using fuse holders or blocks. This can raise concerns during inspections and may not be considered compliant with the code's intent. While it might be technically possible to achieve selective coordination using an inline fuse, the safety and code compliance concerns make this approach less desirable. A better alternative would be to use appropriately sized and coordinated circuit breakers or fuses in approved fuse holders or blocks. This ensures a safer, more reliable, and more code-compliant installation. To elaborate further, achieving selective coordination involves a detailed understanding of the time current characteristics of the overcurrent devices being used. Time current curves illustrate the amount of time it takes for a device to trip or open at various levels of overcurrent. By comparing the time current curves of different devices, it's possible to determine whether they will coordinate properly. The ideal scenario is for the downstream device to have a time current curve that lies entirely below the time current curve of the upstream device. This ensures that the downstream device will always trip or open before the upstream device under any overcurrent condition. However, in practice, achieving perfect coordination can be challenging, especially in the instantaneous region where devices trip very quickly. Firstly, the instantaneous trip settings of circuit breakers can be difficult to coordinate. Circuit breakers typically have an instantaneous trip function that causes them to trip very quickly when a high fault current is detected. This instantaneous trip setting is often adjustable, but it can be difficult to set it low enough to coordinate with downstream devices without causing nuisance tripping under normal operating conditions. Secondly, fuses have a minimum melting time. Fuses have a minimum melting time, which is the amount of time it takes for the fuse element to melt and open the circuit. This minimum melting time can limit the ability to coordinate with very fast-acting circuit breakers. Thirdly, the available fault current at different points in the system must be considered. The available fault current varies depending on the impedance of the circuit. The higher the impedance, the lower the available fault current. This means that the overcurrent devices must be coordinated based on the maximum available fault current at each location. Several strategies can be employed to improve selective coordination. One approach is to use current-limiting fuses. Current-limiting fuses are designed to quickly interrupt high fault currents, limiting the amount of energy that passes through the circuit. This can help to reduce the stress on upstream devices and improve coordination. Another strategy is to use circuit breakers with adjustable instantaneous trip settings. Circuit breakers with adjustable instantaneous trip settings allow for finer control over the tripping characteristics of the device, making it easier to coordinate with downstream devices. A third approach is to use zone-selective interlocking. Zone-selective interlocking is a technique that allows circuit breakers to communicate with each other. When a fault occurs, the downstream breaker sends a signal to the upstream breaker telling it to delay its trip. This allows the downstream breaker to clear the fault before the upstream breaker operates, improving coordination. In the specific scenario described, several factors could be contributing to the coordination challenges. Firstly, the available fault current at the 20 amp branch circuit could be high enough to cause the 225 amp breaker to trip before the 20 amp breaker. This could be due to a relatively low impedance circuit or a high capacity power source. Secondly, the instantaneous trip setting of the 225 amp breaker could be too low. If the instantaneous trip setting is set too low, it could cause the breaker to trip unnecessarily under normal operating conditions or during transient events. Thirdly, the time current characteristics of the 20 amp breaker and the 225 amp breaker may not be well matched. This could be due to differences in the design or manufacturing of the breakers. To address these challenges, several steps can be taken. Firstly, a thorough fault current study should be performed to determine the available fault current at each point in the system. This study will help to identify any areas where the fault current is too high and to select appropriate overcurrent devices. Secondly, the instantaneous trip setting of the 225 amp breaker should be carefully evaluated. The setting should be set as high as possible without causing nuisance tripping. Thirdly, the time current characteristics of the 20 amp breaker and the 225 amp breaker should be compared. If the characteristics are not well matched, different breakers may need to be selected. In addition to these steps, it may also be necessary to consider using current-limiting fuses or zone-selective interlocking to improve coordination. Current-limiting fuses can help to reduce the stress on upstream devices, while zone-selective interlocking can allow the downstream breaker to clear the fault before the upstream breaker operates. The use of inline fuses in a panel is generally discouraged due to safety concerns. Fuses should be mounted in approved fuse holders or blocks, which provide a secure and protected environment. Inline fuses are more vulnerable to accidental contact damage or loosening, which could create electrical hazards. Furthermore, the NEC requires that all electrical equipment be installed in a neat and workmanlike manner. The use of inline fuses inside a panel can be perceived as a less professional and less organized installation compared to using fuse holders or blocks. Therefore, while it may be technically possible to achieve selective coordination using an inline fuse, the safety and code compliance concerns make this approach less desirable. A better alternative would be to use appropriately sized and coordinated circuit breakers or fuses in approved fuse holders or blocks. This ensures a safer, more reliable, and more code-compliant installation. In summary, achieving selective coordination in emergency systems requires careful planning, a thorough understanding of overcurrent device characteristics, and adherence to safety and code requirements. The use of inline fuses inside a panel is generally not recommended due to safety concerns. Instead, appropriately sized and coordinated circuit breakers or fuses in approved fuse holders or blocks should be used to ensure a safe and reliable installation. Remember that calculations, short circuit analysis, and component selection must be performed by a licensed, qualified professional electrical engineer.